Good day, welcome to my online class. Today, let's look at the structural frameworks from strength of materials. But specifically here on this lesson, uh, we're doing strength of materials and structures and five problems for this lesson. Right, this is a framework. What you see here, it's a framework, or we can call this a truss. So a truss is made of several members, and then these members, some of them will be under tension, some of them will be under compression. So these members combined, constructed in this way, will form what you call a truss. So some of these members, this one, a member, let's say a member is, I'm talking about this thing, starting from here to there, it's a member. Starting from here to there, it's a member. In other words, they took a certain piece of steel or a wood. They took many pieces. Let's see here. We've got one here, sorry, two, three, four, five, six, seven, eight, nine. So in this case, this thing is having nine members. So they took nine members and then they joined them together to form this thing here. So this thing in real life, you will see it if you look at the roofing at your home. So those guys, carpenters, when they have to put the tiles there, they will start with this thing. So this is the truss that will be used to support the load. What is the load? The load in real life, we're talking about those tiles. So the load of those tiles will sit on this thing. So, and as well, these arrows that we see here, like this one, it represents the point load. So this thing in real life, it can be maybe a chimney at the top of the house. Right. Now, these members, nine members that you see here, some of them will be under compression, some of them will be under tension. So I'm not used to this display here. Okay. Yeah, so let's go to this introduction page. Now, let's start by understanding what is a tie, what is a strut. So if you have something, that thing can be either horizontal like this, or it can be vertical like this. So if you apply or you take this thing and pull it, apply a force in this manner, and this component is going to stretch, it's going to get pulled. So any member under tension or under stretch, or anything in that state of tension, we're going to call it a tie. So this thing, it can be a rod, it can be a pen when you take a pen, or it can be elastic band when you take elastic band and stretch it. So that thing will be under tension. So anything under tension, that thing we're going to call it a tie. So it doesn't have to be horizontal, it can be something like this. You are going to have a tie there. So in real life, this thing, maybe in class, as you used to see this or at home. This is the roof. Let's say in class we're going to have a rod like this, a round rod, and then at the bottom we're going to hang a projector there. So this projector is going to pull this rod down. So this is the weight. This thing is the projector, which is the weight. It's going to pull this thing down. So this rod now is going to get pulled. So it's going to be under tension. Right. Let's go to a strut. A strut, it's a member in a state of compression. So like right now I'm sitting on the chair. Let's say this is the chair. Those are those feet of this chair, like this. Good. So these feet, this one and this one and this one, they are there for supporting. So to support what? To support your weight together with the weight of this chair there. So once you come and sit on this chair, let's say this thing here represent that leg of that chair. When you sit on top of this chair here, your weight will push those 4 feet downward like this. And then in that way, the ground as well is going to push the feet upward. So this leg is going to be under compression. Your weight will squeeze at that leg. So this leg, I can say now, since it will be under compression, it will be squeezed, pressed down. We can call it a strut. Now, let's check here. We recognize a tie or a strut not by external force. So these arrows that you see here, these are the external forces. So when we determine whether a member it's a tie or a strut, we don't use these external forces, but we use the direction of internal forces. Good. So if you pull, like if you take the pen, that writing utensil that you used to write with, when you take it and pull it on both sides like this, you will see that that pen is not going to really stretch. It's going to stretch, but it's going to stretch a bit. Or when you pull it like that, your hands won't move. So the reason your hands won't be moving is because as the hands apply external force on this thing, the material of that pen will apply the force on my hand in opposite direction. So we call this thing a reaction force or the internal force. So the material of that pen is going to pull back, it's going to react. So as you try to stretch it, it will resist and develop an internal force. So those internal forces will act in this direction. So when we determine whether a member is a strut or a tie, we're going to use this. So if we're going to have a situation where a member is going to have internal forces pointing like this, then we're going to call that member a tie. Right, let's go to the strut. When you're sitting on this chair, you'll see the leg won't go down or the material won't get shrinked or squeezed. So the material will get compressed, but it will move down with a length of microns, very, very small magnitude. So in general, you can say it's not going to shrink. It's not going to shrink. It's not going to be like when you take a sponge, you compress it, it will go down. It's not going to happen there. So the reason there won't be that huge shrinkage or that recognizable shrinkage is because the material, as your weight will be pushing down, this material from the rod made with this rod, so that material is going to resist, it's going to apply an upward force. So we say that according to Newton's third law, uh, this material will apply the same force in magnitude but in opposite direction. So remember I said here the ground or the floor as well is going to push this feet up, then this feet will react and push down. So this red thing that you see there, those are the internal forces. So if you take this thing and put it horizontally like this, so I just took this and then I turn it. Then when you turn it, those internal forces will be like this, will act like this, other one will act like this. Sorry. No. This one is tie. As you can see, these forces are pulling. So I'm on this one. The forces must, the external forces must go in. Must go in, not to pull. They must compress. So they must act like this. They must act like this. So this is the strut that we're talking about. A member under compression, which represented the leg of this chain. Right. So the internal forces are going to be like this, act in opposite direction, like that, opposite direction, like that. So if a member will have internal forces like this and like that, so that member we're going to call it a strut. We're going to call it a strut. Right. So to solve this kind of problem, we have to start by calculating the reactions first. So we have to start by calculating the reactions first. So as I've said that this thing will be used to support the load. So this thing will be used to support the load. That load in real life, as I've said, will be the tiles and then anything that can be on top of the roof. So remember this thing will be placed on top of the wall. So here, this L or this area that we see here in real life, this thing represents the wall. The wall is that thing that is made from the bricks. So this is the wall. When we build a home or a house, we use the bricks. So this truss is going to sit on top of this wall. So now, as this truss, together with the weight of those tiles, they are going to push down, or they are going to push this wall downward. This wall is going to react and push upward with the same force but in opposite direction. So that's why you see an upward arrow here. This L, you'll see upward arrow up. Even on this R, you'll see an upward arrow. It represents upward push by this wall. So that is the reaction. So now, firstly, we have to find how much will this wall push upward, the magnitude of the reaction by this wall. So since here we're going to have what we call the state of equilibrium, we're going to use one of those conditions in order to have this thing not to move, to be stable. The upward forces should be equal to downward forces, and the forces to the left should be equals to the forces to the right, and clockwise moment should be equals to anti-clockwise moment. So to calculate these reactions, maybe we're going to use that one. Clockwise moment equals to anti-clockwise moment. So we're going to take moments here at the left support. So this is the left support. We're going to take moments here. So if you take moments here, let's check the forces that will try or that will tend to rotate this framework in a clockwise direction. So firstly, you're going to have this force here. The magnitude is 100 here, 100 Newton. So we are going to take this force multiplied by the perpendicular distance. Perpendicular distance, all distances must be measured from L. So perpendicular distance will be from from L from here to there. So the distance from here to there is this one. It's 4. So that's why you'll have 100 by 4 plus another force that will try to rotate this thing in a clockwise direction is this force here. Then you take this force, which is 60, you multiply it by perpendicular distance. Perpendicular distance will be the distance from here to there. So the distance from here to there will be this. Look here, from here to there is 4, from here to there is 4. Therefore, it's going to be 8. 4 plus 4 is 8. Another clockwise force will be this 20 here, which is this 20 multiplied by the distance from here to there. So this distance is going to be 4 plus 4 plus 4, which is 12. So that's all for clockwise forces or moments. And then anti-clockwise moments is going to be this upward force, which is R. This R will try to rotate this framework in an anti-clockwise direction. So that R is this one. This 12 is going to be the distance from here to there. We already said that this 12. And from there, you calculate the reaction. You make R the subject of the formula. Then R will be equals to 100 multiplied by 4 plus 60 multiplied by 8 plus 20 multiplied by 12 all over 12. You will get 93.3, as you can see here. So from there, now we change. We want to know, okay, now we just got the reaction R, which is 93, meaning that this wall here is going to push upward with the force of 93.3 kN. So we know the reaction here at R. Now we have to find the reaction at L. So to find the reaction at L, you can take moments at R, or you can use that state of equilibrium condition. Upward forces will be equals to downward forces. So it's really up to you. Then if you consider upward forces, you're going to have L plus R. R, we just got that R is 93.3 equals to downward forces. We'll have this force here, which is 100 plus this force here, which is 60 plus this force here, which is 20. So from here, are they all downward forces? You only have three forces here. Then from this, you can find the L. You can find the L. So L will be equals to 100 plus 60 plus 20 minus 93.3, 86.7. So which is this answer that you see here. But anyway, you can take moments at R, which is here, to calculate this. So because of time, I'm going to jump that step. I'm not going to do it. Right now, we got direction here. Direction on this side will be 86.7. So now we've just calculated the reactions. Now we're going to draw a vector diagram. So we're going to draw the space diagram. So that space diagram is named the space diagram because we use spaces between the forces to construct it. Right. Yeah, maybe let's go to this. This thing, which is the same thing as that one we did before. From those calculations, we got that the reaction on this side is mm, yeah, if I'm not mistaken, 93.3, 93.3 kN. Yeah, I want to put 15 here, but it's doing its own thing. Okay, 93.3. Kn. Let's leave it like that. Then on the other side, we got 86. 86.7 kN. Those are the reactions. Okay, so now our task in this problem is to find how much this member is going to carry. So I remember I've shown you the members before. So each member is going to carry a certain amount of force, or is going to have a share of the load. So that load of the tiles from this roof will be supported by these members. So these members are not going to carry the same load. So each member will carry its own share of the load, which is not going to be the same. So maybe a certain member will carry 10 Newton, another one 5 Newton, and so forth. So that's what we want to find now. So that's what we are trying to find now. Let's see the question. Graphically determine the magnitude and nature of forces in each member. So we're going to find the forces in each member. And then we have to find the nature as well. I mean, the nature meaning that we have to find whether that particular member is going to be under compression or is going to be under tension. So in this kind of scenario, if we've got this kind of loading, we have to find whether these members will be under tension or under compression. Right, so this thing, we call it space diagram. So what you see here, this is a space diagram. Where you will finish there. This is the space diagram. So we call it space diagram because we're going to have space here. Look here. So this space here. Okay, the space between this force and this force, which is this space here. This space, we're going to call this, we're going to give it the name. So we're going to call it A. This is space A. Starting from here to there, all this space here, we're going to call it A. So we name the spaces between the forces, like now here, between this force and this force, there is this space here. So we're going to give this space a name. So we're going to call this space B. Again, between this force 60 and 20, there will be a space here. So this space, we're going to call it C, and so forth. Between this force and this force, this space is named D. Between this force and this force, the space will be called E. So we name the spaces between the forces. So here we're not going to have we're not going to have E, F, G. No, we're not going to have that. We name the spaces between the forces. You have to check where is the force. Here's the force here. From there is another force, which is direction force. So this space between these two forces, that space, the whole of it, it's E. So those spaces, they are already named for you. So if they are not named, you have to do that yourself. Luckily enough, in this question, they have already named the spaces for us. Then the spaces we're going to have, the can say the external spaces and the inner spaces. These are the inner spaces. So this inner space's name is called F, G, H, blah, 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 blah. So we have to name those spaces as well. Now from here, after naming the spaces, we're going to draw now what we call the vector diagram. I will try to draw it on the same page. I will try to draw it on the very same page. I'm going to draw what? I'm going to draw what we call the vector diagram. We're doing graphical method here. Determine the magnitude each member will carry. So there are other methods that you can use, but I think it's for our syllabus and 5 strength. We use graphical method, which is this vector diagram that I'm going to draw now. So this vector diagram is going to have the magnitude and the direction. We know a vector has a magnitude and the direction as well. So what we're going to do here is that we're going to draw the lines parallel to the forces. So the lines on the vector diagram must be drawn parallel to their corresponding lines on the space diagram. So from this space diagram, we are going to use these forces from this space diagram to draw the parallel lines here. And the combination of those parallel lines will be called the vector diagram. Okay, to draw that, we can start with any force here, but normally we start with the known forces. Then those known forces normally will be the external forces. So those external forces, I'm talking about this force 100, this force 60, this one, and this one. We know the magnitude of these forces. So when you draw this vector diagram, you can start with any force. It's really up to you. But make sure that where you start, you must move clockwise in this way. If you start with this force of 100 Newton, oh wait. I can see here I have Newton, but the reaction is K. Yeah, if this is Newton, then this will be Newton. No K here, no K. Right. So if you start by drawing a line parallel to this force of 100 Newton, the next line must be this one of 60. The next line must be this one. We move clockwise like this. So you mustn't start with this force of 100. After that, you move to this L, which is 86. You will be moving anti-clockwise. So make sure that where you start, you must move in a clockwise direction. So like if you start with this force of 60, the next force that you must draw, it must be 20. Then that will be clockwise. Don't start with 60 and then draw a line that will represent 100. So you'll be moving from 60 to 100. So this movement will be anti-clockwise. So always make sure that you move clockwise. Right. You're going to have your ruler. Here's the ruler. Yeah, you'll come up with your ruler like this. I'm putting it vertical because these forces that I'm going to start with, all of them, they are vertical. This is vertical. Remember here, I'm going to draw a parallel lines. So parallel lines. So since these lines that are vertical, it means that whatever lines that I'm going to draw here, they must be vertical. So, okay, before you draw here as well, you have to choose the scale. You have to choose scale. So when you choose the scale, yeah, this or keep this in mind. The sketch that you will have to produce at the end of the day must be big enough. In other words, you must make sure that your sketch must fill the page or must occupy at least 80% of your page. Don't make your sketch too small. So if you make the sketch too small, the answers that you will get, they won't be that accurate. So to get accurate answers, You must make sure that your sketch is big. Right, I can see here 100 Newton. If I say 100 Newton equals to 1 centimeter, I think it's going to be long. Okay, let me just say 20 Newton will be represented by 1 centimeter. So that is my scale. Then if I use this scale, then if I use this scale, I want the zero to be at the top. Trying to turn this ruler. Good. I hope it's vertical, this ruler now. Right. So in this case, 1 centimeter, meaning that from here to there, which is 1 centimeter, will be equals to, or is going to represent the 20 Newton. So if I move another 1 centimeter, it's another 20 Newton, meaning that this length from here to there represent 40 Newton. So from here to there 60, from here to there 80, from here to there 100. So this thing represent this line of 100 Newton. Then when you check this line is between space A and space B. Now, because this line of 100 Newton is located between space A and space B, then we're going to call this line AB. So we're going to say this line is AB. So this point there is going to be A. I can use small letters. And then this one is B. Now, as I've said that you must move clockwise. And then as well, don't say this line is BA. So when you say BA, it's like you're starting here at B coming to A. So you'll be moving anti-clockwise. Always move clockwise. So you start here, you must say A to B. You move clockwise. You move clockwise, A to B. So that's why we say this line is AB. We started A, we moved to B. Now, let's go to the next force. Moving clockwise, it's 60 Newton. So 60 Newton on this diagram is going to represent, it will be equals to 3 centimeters. So I'm going to draw a parallel line, a line parallel to this. And then that line, I'm going to make it to have a length of 3 centimeters. 60 Newton will be equals to 3 centimeters. Then you can put it here and then draw another line 3 centimeter going down. Must be in line with that, with this one. Yeah, it's not exactly giving me. It must be in line with this. It must start here, but it doesn't want to do that. Let me see if I can shift this ruler a bit like this. Yeah, let's leave it like this. You draw 3 centimeter. That 3 centimeter will represent this fascia 60. Then this fascia 60 is between B and C. So this line that we've just drawn, which represent the 60, that 60 which is between B and C. So this line we're going to call it BC. So we're going to call this line BC. So this will be C. Then from there we move to the next force, which is 20. Then I'm going to draw, since this force is acting down, I'm going to draw another line going down. Then now this line I'm going to make it 1 centimeter. Remember I said that here, remember we said that 20 Newton equals to 1 centimeter. So I'm going to draw a line which will represent 20 centimeter going down, but at the length of that line we have to make it 1 centimeter. Then I draw another line there from here to there 1 centimeter. Then we're going to call it that line, or that force is between, that force of 20 is between C and D. So this line which represents that force of 20, or this line we're going to call it CD. So we're going to call this line CD. Right, please ignore the fact that these lines are not straight. They should be straight. Let's assume we're straight line like this ruler here. These things, they are not supposed to be misaligned, as you can see there. Right, we're not yet done. We're remaining with 2 forces, which is this reaction force and 93.3, and then this reaction force 86.7. Now these forces, they're acting up. And now we've just drawn this force at 20. Now we have to come with this force R. Then this force R is acting up, then it means that we have to draw an upward line that will represent that R. So we're going to draw an upward line. That line will represent the R. So let me put my ruler in order. Yeah, meaning from that D, we have to draw an upward line with the magnitude of 93.3. Yeah, remember our scale. 93.3 will be equals to how much? 93.3 divided by 20. 4.665. So 93.3 will be equals to 4.6 centimeter. So you'll measure from here 4.6 centimeter. From D, this is 1 centimeter, 2, 3, 4. This is 4.5, 4.6 will be somewhere there. So we're going to draw a line from D up there. So let's draw that line. from D to there. So where this line ends, remember this line that I've just drawn there, it represents this upward force 93. Then this upward force is between D and E. It's between the space D and E. Therefore, that upward line that I've just drawn now, we're going to call it DE. So where this line ends, it's going to be E. Right now we go to the last force. The last force, which is this one here, 86.7. 86.7 divided by 20 equals to 4.3. Since this thing is going up, then it means that from that point E, we have to draw an upward line. That upward line will have to be 4.35 centimeter. Let me see something. Seems like something is not right here. Yeah, something is not right. Something is not right. Okay, it's fine. Let's not go back to reaction. This reaction at 93. So we said that 93.3 divided by 20, it's 4.6. 4.6. Yeah, so we're supposed to draw an upward line from D 4.6 up. So remember I said that this one is 1 centimeter. So if from here to this 1 centimeter, this one will be like 2 centimeters. So the length of this line DE is not right. So the length of this line DE is not right. But it's due to the fact that I'm stretching this. I'm zooming this thing in and out. So that's why we're facing this kind of problem. Get that thing. Remember, if you take this ruler now, next to here, initially when we plotted point C to D, this thing, it was equals to 1 centimeter of this rule, but now it's no longer there. It's because of the zooming. So, but now let me make sure that I take this thing back. Let me zoom it in such a way that it will be equals to 1 centimeter here, like this. Yeah. So we said that that upward direction of 93 will be equals to 4.6 if I'm not mistaken. Yes. Then we'll draw measure up from here upward 4.6. This is 1 centimeter, 2, 3, 4. 4.6 will end somewhere there. Good. This is right now. So E will start from here up to there. So where this line ends, it's going to be E. It's going to be E. Erase this one. Right from there, we go to this reaction of 86.7. So 86.7 divided by 20, 4.3. So we have to draw an upward line again with a length of 4.3 centimeter starting from E. So the line that I'm going to draw now here is going to represent is going to represent this reaction, and then that line is going to be between space E. Linear 86 is between space E and A. So therefore this vertical line that I'm going to draw now, we're going to call it EA, because this 86 is between E and A. But as you can see here, actually that line is already there. But it's fine, you can draw that line from E, you measure 4.3 going up. So as you can see here, this length is 4.3 already. From here to there goes 1 centimeter, 2, 3, 4. 4.3 will be there. So from E to A is 4.3. So you draw a line from here upward, 4.3, you will end at A. Good. So now I've managed to draw all, or to find the position of all the external forces. Now, as you can see from this diagram, we have A on this vector diagram, we have B is here, C is there, and E is also here. So the only letters that we don't have now, or spaces that we don't have now, is space F, G, H, and I. So we have to find the locations or the position of those letters F, G, H, I. So let's start here. You can start anywhere. You can start here or here. It's up to you. Right. So to find the location of of F, we are going to use the adjacent spaces, the neighboring spaces. Like here, the adjacent space of space F. This is space F. So this is space F. Neighbor next door. Neighbor of F is going to be A. A is next door. This space here is E. This space here and G. So H is not the neighbor of F, because to move from F to H, we have to jump G. Or to move from F to I, you have to jump this and this. So I is not the neighbor of F. Since H and F are not the neighbor, even this B here is not the neighbor of F. So we're not going to use that one. So we have these three spaces that we can use, which is A, E, and G. But we only need two spaces. We don't need three actually, we need two. And then make sure that those two that you choose, they must already be located or available here on this vector diagram. Remember, on this vector diagram already we have point A, E, B, C, D. So from these three spaces, we need two. We are going to use two. It's either we're going to use A and B. This is E. A and E, or G and E, or blah, blah, blah. Any two. So we'll see how to pair them. But whatever that you use or you choose, it must already be here. So as we check here, G, it's a neighbor. But G, we don't have G here at the moment. So this G thing, we're not going to use it at the moment because it's unknown. We don't have the location of G on this vector diagram at the moment. Therefore, we're not going to use G. So the spaces that we're going to use now is going to be A. Yes, we have A. This is A. Then we're going to use E. This space here is E. Yes, we have E on this. We're going to use that. Now, since you are looking for F, then we're going to do this. We're going to look from A to F. From A to F. Remember, I'm trying to find the location or the position of F here. So from A to F, or F and A, they are separated by a line which is moving at an angle of 45. So that means as well, we're going to draw a line from A moving at an angle of 45. So we're going to draw a line parallel to this line. So this line which separates A and F, it's moving, is inclined at an angle of 45. So from A to F, we have a line at an angle of 45. Therefore, you'll come at here at A, then from A to F, there is a line moving at an angle of 45. Then you'll come there, A, you'll draw a line parallel to this. So that line that you must draw here from A must be parallel to this. So it must move with the same angle as this. So now that's where protractor comes in. You come and take your protractor and put it there, like this. Then from there, you mark 45. You mark 45. So this is 0 here, 10, 20, 30, 40, 45. So that is 45. So you can draw a line there from this 0 here. That line must be at an angle of 45. But let me use a dot, because yourself you won't be able to do that. Yourself you have to make a dot. You're going to, here at 45 degrees, you put a dot like this. Then after that, you remove this protractor. Then after that, you draw a construction line. Construction line meaning a dotted line. So you're going to put a dotted line from here, crossing that point A like this. So this line is parallel to this line. So this line is moving at an angle of 45. This line as well is moving at an angle of 45. So as you can see here, this 45 is measured from this side, from the right hand side to there. Remember, this is your dot or your joint. So I'm doing this because some of you will be confused. Or this 45, must we measure it from this side or from this side? So we are going to measure it from this side, because as you can see, this 45 is measured on the right hand side of this joint, of this dot here. But when it comes here, when we're going to draw a line parallel to this, we're going to measure your angle from the left hand side. So you'll put your protractor like this and measure 45 from here. You'll have 0 here, 10, 20, blah blah blah. 45 will be there. You will measure from this size in this case, because this 45 is measured from the left hand side of this joint. So when we'll measure from the left hand side. So this time this angle 45 will be measured from this right hand side of this dot here. So that's why we're going to put a protractor here. And then 0, we measure the angle from this side. From this side to that side there. But despite that, remember here I said that we draw the parallel lines. So if you measure 45 from this side, okay, you will make a dot here. This should be 45. Then you remove this protractor. You draw a line like this. Now the problem of this line is that this line is not parallel. This line is not parallel to this. Remember, the line that you must draw must be parallel to the line AF. So this dotted line, this one is not parallel to this, but perpendicular. So we draw parallel lines here. We don't draw perpendicular lines. So that line will be wrong. Good. So now, as I've said that to find the position of F, we need two spaces. I said that we're going to use A because already we have A here. Then we're going to use E. This space here that you see here, this one is still falls under space E. Remember, space E starts from here to there. This whole space is E. So this part as well, it is still under E. So now, from E to F, when you move from this E to F, there is a horizontal line. So E and F, they are separated by horizontal line. So from E to F, it's horizontal line. So you'll do the same thing here. We don't know where it's F at the moment, but what you know is that from E to F, there is a horizontal line. So we're going to draw a line from E, the horizontal one, like this. We normally draw it on both sides. We're going to draw a horizontal line from E, and then where these two lines meet is going to be point F. How did we get this point F? We've used the adjacent spaces, which is A and E. From A to F, there is a line at an angle of 45, and that's why we came here and draw this line at an angle of 45. We came to A. From A to F is line at an angle of 45. So you come here, start at A, you draw a line at an angle of 45. You project it on both sides. Then after that, you come to E. From E to F, there is a horizontal line. And that's why from E, which is this point here, from E, we draw a horizontal line. So where these two lines meet, they're going to give us the location or the position of F. So this is point F. This is point F. At this point F. Right, these things, they are the construction lines. These dotted lines, they are the construction lines. Right now, we're done with point F. We've managed to find the location of point F. Point F is here, where these two lines meet here. Okay. Now let's go to the next space, which is unknown. The next space is G. So let's go to G. G, let's start by finding the adjacent spaces of G. We're going to have this space here. It's a neighboring space, is E. And then this space, this side is F. And even H as well. But H, at the moment, we don't have H on this diagram. We don't have H. So we're not going to use H. We're going to use F and E. So maybe let's start with E. From E to G, there is a horizontal line. So we will go to E, which is this point here. We're going to draw a horizontal line. Is already there. This is the horizontal line from E. Then again, we'll go to F. From F to G, and there is a vertical line. Then we're going to draw a vertical line from F. We're going to draw a vertical line like this. Then where those two lines meet will be point G. Which lines meet here? I'm talking about where the horizontal line from E meets the vertical line from F. Where they meet, it will be point G. So that horizontal line from E, which is this, it meets the vertical line from F here. So those two lines meet here. So meaning that at the very same point where you see the red dot, that point is going to be point F and G at the same time. So this point will be F and G. So F and G are located at the same point. Why? Because to find F, you draw a line from A to F. It's a line at an angle of 45. Here's A. From A, you draw a line at an angle of 45. Then from E to F, you draw a horizontal line. From E, this is E, draw a horizontal line, they meet here. So the same thing, to find the G, you draw a vertical line from F. From F to G is vertical line, here's vertical line from G. And then from E to G is horizontal line. This is E, you draw horizontal line from E is this one. So where those two lines meet, vertical line or horizontal line meet, it will be point G. Now let's go to page. And the neighbors of H adjacent spaces, it will be B and G. B and G. This is G, this space. Even I qualifies, but the problem with I is that we don't have I at the moment. We don't see letter I, so we can't use I. Right. When you move from B to H, you see horizontal line. B and H, they're separated by a horizontal line. So we're looking for H. What do you know is that from B to H, we're going to have a horizontal line. So you'll come to B. Here's B here, and then draw a horizontal line. You project it on both sides. Draw horizontal line. Like this. Then from G to H, there is a line moving at an angle of 45. Therefore, as well, now we have to draw a line parallel to this. The line that we must draw must be parallel to this, must move at an angle of 45. So we're going to draw that line from where? From G. From G to H, or between G and H, there is a line at an angle of 45. So from G, which is this, we're going to draw a line at an angle of 45. So the protractor comes in, yes, point G. You put your protractor like that, Then now this 45 is measured on the left hand side of this joint. So here is the joint. The angle of 45 is formed by this line and this line. So here's the included angle. I'm checking this joint here. So this joint, I mean this angle of 45 is measured from the left hand side of this joint. So as well here, it means that our angle will have to be measured from this side. So this is 0 somewhere here. You measure 45. 45 would be, you can mark it here. After marking 45, you remove the protractor. Then you draw a construction line from this red line. Then angle of 45, it will have to cross there, like this. Then where these two lines meet will be point H. How did you get point H? You'll see from B to H, there is a horizontal line. So this is B. That's why we've drawn from B, we've drawn the horizontal line. Then from G to H, there is a line moving at an angle of 45. That's why from G, this is G, we've drawn a line at an angle of 45. So where those two lines meet, which will meet here, where these two lines meet will give us H. So this point here is going to be H. Okay, that is H. Then now we're only left with space I. We've got all letters or all spaces except I. So now let's find I. To find I, you can use any of these three letters since we have all of them right now. The adjacent space of I is C. We have C, this is C. Another adjacent, take E, this side is E. We have E, this is E here. And then another adjacent, it's H. Then we have H here. So now it will be up to you. You just have to choose two, any two. But I would like, myself, I would like H and E because we don't have to use any protractor here. If you use this side, which is C, as you can see, C and I, they're separated by a line moving at an angle. You will have to use protractor. But from H to I, it's a vertical line. Therefore, you just have to come to H and draw the vertical line like this. From H, you draw vertical line. Then from H to I, it's vertical line. Now from E to I, it's horizontal line. So you'll go to E. This is point E, remember. You draw horizontal line. The horizontal line is already there. So where this vertical line from H, meets horizontal line from E. This is vertical line from H meets horizontal line from E. This point, where they meet is going to be point I. So point I is going to be there. So this is point I. Good. We're done. So we've got all spaces A, B, C, D, E, F, G, H. We've got them here. We have all those points. So now we just have to finalize your diagram, make these lines solid. Remember what we are seeing here, the construction lines. And then you have to erase where you have to erase. I'm not sure if I will be able to erase, but I will try. Yeah, but first of all, we're going to join this diagram like this. You will come here and check here. This member here, from here to there, it's AF. It's a member. So you'll join the AF. You're going to make A, A, and F. We're going to join AF with a solid line. Can use a different color now, which is going to represent the final vector diagram. So I've chosen sky blue color. Then I'm going to have a solid line now. I'm going to have a solid line. So I'm going to draw a line from here to there. Then I'm done with this member here. I come to this member. This member here is between E, this space is E and F. So I'm going to join EF. EF, it represents this member from here to there. So I'm going to join EF. Remember, this is E. This is E here. So I'm going to join from E to F. Then I come to this member here. This member here, FG is between F and G. So I'm going to draw a line from F to G. This is F to G. Oh, F and G are on the same point. So yeah, actually the length of that line would be 0. Okay, what is the meaning of that? It means that this member here is not going to carry any load. Actually, it's going to be useless. It's not going to get stretched. It's not going to get compressed. It's not going to carry any load. It's not going to transmit any load. So it's a waste of material to put this thing there. It's totally a waste of material. It's useless, member, this one. Right, from there, let's go to this member. It's between G and H. So I'm going to draw a line from G to H. This one. From there, let's go to this member here. It's between G and E. This member from here to there, between G and E. So I'm going to join G and E. It's already joined. Remember, this is G here. This is E here. Now let's go to GH. Is it joined? Yeah, GH is joined. Now let's come to this member here, which is between B and H. So I'm going to draw join point B and H. So this is B, this is H. From here, let's go to this member here, which is between H and I. H and I. So I'm going to join H and I. H and I join. From there, let's go to this member here. Is between E and I. E and I, they're already joined. Between E and I, this one, there is already a solid line. From there, the last member, this one is between I and C. So I'm going to join I and C. So from I to C. So these ones we've joined them at the beginning when we're drawing those external forces. So your final diagram is going to be this blue line. Let me see if I can erase this thing. These things are the construction lines. So I'm only able to erase this. So the dotted lines I can't. But I will try another technique and see. So at the end of the day, you can remove the construction lines, but if you made them too light, there is no need to erase them. You can leave them. Yeah, I'm trying to erase these dotted lines. Uh, Let me just move it like that. Mm. Yeah, good. Finally, you'll have this. Finally, you'll have this. Remember here is F and G. Here you'll have H. Good. So what we are seeing here is the same as this from where's the memo? I have memorandum somewhere. It doesn't want to appear. Oh, I had a certain slide here with the memorandum and answers. Right now it doesn't want to appear. Doesn't want to appear. Let me see. Or is this one? Yeah, so what we've seen there from that other page, it's exactly this. So this one I got it from the memorandum, which is exactly the same thing as that one that we got there. Some of you think that by plotting this vector diagram, you think that you've answered the question. No, we didn't answer the question. The question is to determine the magnitude in members. So by just drawing this, you didn't determine the magnitude. You didn't tell us that the member AF will carry this much, member what will carry this much. So must tell us that this member from here to there, which is AF, you must tell us how much load is going to carry. You must tell us how much is this member GH is going to carry. All these members. So like as they did here. So if you want to know how much will member AF carry as I've shown you on this. This is member AF. So if you want to know how much will this one carry, you just have to measure from A to F. You measure this length from A to F, then maybe you will get, I don't know, uh, maybe you'll get 6 centimeter. So you'll come with a ruler and measure there. You'll come with a ruler and measure there. Because I did the zooming and what, but you should get 6.1 maybe. Just that you might not get it now because of those zooming as I showed you earlier. Yeah, you must move your ruler to exactly the angle as this, then measure like this. Yeah, so you should get 6. Roughly, you should get 6, maybe 6.1. We'll measure here, maybe get 6.2, 6.1. So you take that length. If it's 6, you take that 6, you multiply it our scale. Remember we said that 1 centimeter equals to 20 Newton. Then you take that 6 centimeter, you will multiply it by 20 to get the force. And that 6 multiplied by 20, you will get this 122. So this 122 here, you will get it from maybe saying 6.05 multiplied by your scale 20, then you'll get that 122 maybe. So that's what you must do. So you repeat this thing throughout. You repeat this thing throughout. So like if you want to know how much will the member, let's say IE, how much will member IE carry? IE, we're talking about this member here. This member is between I and E. So if you want to know how much this member will carry from here to there, we will come to this vector diagram and measure from I to E. Measure from here to there. Maybe you will get 3.5 centimeter. Then you take that 3.5 centimeter and multiply by 20, or maybe you'll get this. That's how you must do it. So due to time, as I can see, this is already long, this video. And now let's go to the nature. Remember they said you must find the magnitude and the nature. So to find the nature, I'm talking about this thing that I've started with. We have to determine whether the member will be a strut or a tie. So this S here stands for strut. Then strut is a member under compression, or any member in a state of compression, it's a strut. So as I've started with these things, I think, yeah, these ones now. So remember I said that we determine the nature by this. I spoke about it. Let me not waste time on that. For now, let me go and redraw the arrows on the other page that we're working on. I'm going to draw these things. Where is that page? Yeah, let me use this space. So we said that if the arrows are pointing like this and like this, we are going to call that thing a tie. Then if we have arrows pointing like this, we're going to have a strut. Good. So how are we going to determine whether a member is a strut or tie? We've got different methods. But the removal method is one of them. We've got this one. But the removal method, sometimes you will get confused, more especially if the framework is complex. So this one is the most reliable one. Let me show you how it works. So you will go to any joint. So you will come here and choose any joint. So to choose any joint, we prefer the one that will have less members. Let me try to erase these things. Right, we can use any joint, but I've had some authors saying that you must start where you have less members. But if you are not new to this, if you are more experienced, there is no need for that. Like here, you will have this one and this one and this one. You will have three. You can say three forces or three members. You can start there. It's unlike here. Here you'll at this joint, at this point here, you'll have one, this line, two, three, four. You have about four lines or four members. So here you'll have one, two, three. Okay, it's fine. Let's start where you have less members. But as I've said, you can start any point. You are not forced to start there. If you want to, you can still start with this joint here. So the joint we're talking about this point. This is where these members are joined. So we're going to consider the joint. So, but anyway, let's start here at this joint. So you can make a cycle like this. If you make a cycle like this, this space in between this space, this side is still the very same space A. This is still A. And then this space is still the very same space E. This space here is still the very same space F. Right. Once we have this, we are going to start at any letter here. But where you start, make sure that you move clockwise. So if you start at the letter E, you must move from E to A, from A to F, clockwise. Don't move from E to F. Don't move from F to A. You will be moving anti-clockwise. Now, you will start moving. Anyway, you can start anyway. Let's start at A. From A to F. From A to F. You move clockwise. You will come here on this vector diagram and check. When you start moving from A to F, which direction are you taking? When you move from A to F, you will be moving downward like that. So because when you move from A to F, you move downward. Then draw a downward arrow. Draw a downward arrow. So I hope you don't confuse. Draw downward arrow. And after that, you are done. You come here. You move from F to E. From F to E, you come here again. You check here. When you move from F to E, you will be moving in that direction. So you'll come here from F to E, you will draw a line, you will draw direction in that way. Then when you move from E to F, which is this line here, from E to F, already there is an upward direction. You don't need to do it, but you will see from E to F, you will be moving up. From E to A, sorry, it's from E to A. When you move from E to A, you are going up. So that's why this force is pointing up. From A to F is down. So that's why you'll have downward direction. Then from F to E, from F to E, this direction. So that's why here you draw this direction. So now if, check here, check these arrows. Where are they? Yeah, these arrows doesn't point in the same direction. Look here. If this one is pointing in that way, this one will point in opposite direction. If this one is pointing in that direction, this one will point in opposite direction. So the same thing applies here. On this, towards this end, the arrow is going down. So if it's going down, we're talking about this member here. When you consider this member, on the other end, direction of the arrow is downward. Then the other end, which is this, the direction will be opposite, will be up. If this one is going down on this side, on the other side will go in opposite direction. So the same thing here on this other end, now on this member here, this member. When we check this blue member here, on this other end, the arrow is going towards east. Then this other end will go in opposite direction like this. Then we said that if the arrows are, let me zoom this, make it smaller. If the arrows are like this thing that you see here, the very same thing as this one. If the arrows are like this, then we're going to say this member is a tie. So that's why this member is what is FE. That's why when we come here to FE, yes, FE is what? FE, it's a tie. Then if the arrows are like this, which is this one here, which is this member here, The other one is going up like this, the other one is going down. So if the arrows are like this one, we're going to have a strut. So that's why this is what this is AF. That's why AF here will be S, will be a strut. And we'll go to the next joint, another joint. It will be the last one since you can see this video is taking long. Due to that, I'm going to the last point. Let me use this point that is already circled here. This space here, it's B. This one, this side is C. This one is I. This one is H. I made my circle a bit smaller. Right. Look, you can start anywhere. But where you start, make sure that you move clockwise. So if you start at C, you must come to I. Don't go from C to B, you'll be moving anti-clockwise. So from C to I, let's go to this space diagram. Check from C to I. From C, this is I, if I'm not mistaken. So from C to I, you'll be taking this direction. So I'm going to draw the very same direction like this, up. And then if this on the other end of this member here, if on the other end the direction is up, on the other end direction will be down. Okay, you move now from I to H. Let's come here and check from I to H. From I, which is this, to H, get down. So from I to H, you will be going down. So you'll come here again. From I to H, get down. You draw downward direction. So if this one is going down, this other end will go up. Then from there you come here from H to B. You come here and check from H to B. From H to B, you will be moving in this direction. Then you come here, you draw that direction. So if on the other end direction is like this, the other end direction will be opposite. So now this member BH, this one, as you can see, the arrows are like this, So it means that the BH is going to be strut. BH is going to be strut. So with this one, BH strut. Then when you go to HI, HI is like this. Those arrows are there like that. If you take this thing and put it vertical, you will have this. You will have this. If you take this to vertical, you will have this. So this thing, which is this thing that we have there. So HI is going to be a tie. HI is going to be a tie. Here is the tie. HI, it's a tie. And then from there you have this one. The arrows are pointing away from each other. Is this one. This one they're pointing towards each other. This one away from each other. It's like this. This one is pointing like this. This one like that, away from each other. Therefore, it's a strut. What is a strut? Strut is CI. So CI is going to be strut. CI, this one. CI. It's a strut. Right, good people. Thank you very much. See you in the next lesson.